Okay, it's 4 o'clock. Welcome to the computer error engineering course. This is probably one of the first, one of the few times that you're going to see my face. I will disappear in a few minutes. I asked people whether they could hear me, and they said, yes. Can you see me? All right. Oh, wait a minute. Yes. Share video. Okay. I think you can see me now, for sure. All right. So this is going to be tough. And I put myself in your shoes. It's tough for you and it's tough for me. But we're going to be doing our best. Now, what I suggest, if at any point you don't hear me or you don't see the slides or the screen, let me know, okay? Because this is the first time I'm using this, and I'm sure I forget to share the screen. I forget to share the what is that? Whiteboard, etc. So send me a message, and I'm gonna fix it. Okay? Did you hear me? Yes. Excellent. All right. Good. So the reason I start with my labs the first week, even before the lectures start, is twofold. One is this particular lab, this particular section already has 2 Mondays, Victoria Day and a civic holiday, that basically you're on holiday. And of course, the university set some days aside at the end of the term to account for those missed days. My intention is not to use those days, so I would like to proceed. This is why I start doing this thing on the first day before even I have a formal lecture with you. Okay, now we're going to go, the first thing we're going to do is to go through the syllabus quickly. The syllabus has been posted on Blackboard, and notice that it says draft, because in the first week things can change. They're not going to change dramatically. It's just that, you know, the email of the GAs were wrong, you know, stuff like that. And I still haven't decided that which GA is going to do which specific lab. You know that because you're in lab 50, this is lab 53. Because you're in lab 53, you know who your GAs are. But I'm going to split you guys. Right now there is 110 people. There's 110 people in this particular 104 people in this particular lab, and one GA cannot handle marking, you know, your assignments. So you are going to be split into probably 2 groups of around 51, 52, and then each one of you is going to be assigned a particular GA of the 3 that you have in your list, or maybe 4 you have in your list, and they're going to be the people who are going to, that individual is going to be the person that is going to mark your homework, and you can email him or her in your case and ask questions, etc. Okay. So that's why it says draft May 10. That's going to change as you know, minor changes come along. Okay, so let's go through this document. Not this one, not that one. Okay, I'm assuming that's a yes because I can't see the screen myself. Okay, so can somebody say something, please? Yes or no? Because I can't see the Blackboard thing.
Yeah, yes, sir.
Okay, very good. Thank you. Thank you. Anytime that there is a problem, raise your voice. Sometimes I can't see your hands, like now. Okay, so notice that I'm adamant about saying go with the lab. And I just told you why, because the labs are going to have their own GAs. They're going to be marking your papers and answer your questions, okay? And the midterm and the final later on is going to be scheduled according to these four lab sections: lab 51, lab 52, which is not you. You are 53 and 54. In your case, you're 53, and in all likelihood, you're a fourth-year student. There may be occasional, situation where the third year may be sitting here, or one of the fourth-year people may end up in a third-year class. But this is identical material. Don't worry about it. But in all likelihood, you're a fourth-year student. Now, I have my office hours here, and let's see now. Okay. Notice that we have 7 GAs. 4 of them are working with you. They're down here, but specifically which GA is responsible to you or the other way around, I'm going to announce that later. Okay. Their office hours are here. Now, I'm going to be following these 2 textbooks. Now, I got messages from people saying that how do you get them, etc. Well, that's up to you. Of course, I also got a message from the bookstore, I think on Friday, and they were asking me that apparently people contacted them and they didn't have a record of this. So I told them, look, these are the books that I've used in the past 15 years. So order 50 of each. And they have done that. They may be here, I don't know, a few days, but it's up to you. Nothing is mandatory in this course except for writing the test and writing the final. Okay, homework is not mandatory. You don't have to do it. It's just 10% of your grade. So it's up to you. So whether if you want to get this book from the bookstore, from Amazon, from a friend, if you want to download the pirated version, which I don't condone, but anyway, it's up to you. All right, I follow these 2 books. Now, the first one, we're going to start the topic with the first book, the course with the first book, okay? So about 7 weeks of the course, 6.5 weeks of the course, 7 weeks of the course, deal with finite element analysis. And then after that, you might as well forget about it. You can burn your notes, burn your book, whatever you want. You're going to move to a different topic. The final exam is not going to be cumulative, so you're going to be tested on the material for finite elements of the midterm, and then we move on to something else toward the last 5 weeks of the course. Okay. Now, the question came up is, can I use my CATIA that's on my laptop or, on somewhere? And the answer was sure, but for learning purposes, of course you can use it. The problem is that when it comes to doing your homework or writing a midterm or a final and uploading these into Blackboard, that you may use a version that the GAs cannot open. So it's not a suggestion. I ask you because if you run into a problem, you ask for it. Homework, midterm, of course, and final, these to be done on the official CATIA version that's a university website. And the process of logging into it, you can do it through the virtual lab, and that's how I do it in general. But there's also, apparently, there's another version of it that I posted. The instructions for you on the resources section of Blackboard. I'm assuming everybody's hearing this stuff. Okay. All right. So this is the course schedule, and it's tentative. I mean, there may be changes, minor changes here and there. Now, every lecture that I do, presentation under, this is lab 1, right? Right here, the first item. And first 50 minutes, syllabus, and then we talk about finite elements, and then we take a 10-minute break, and we move on to the next 50 minutes. Today, we're going to be stopping before the end of the hour. The labs are supposed to be 3 hours. I'll talk about that in a minute. My intention is to discuss these topics. For example, let me show you something. Probably I've already tried it. If I go to this item and click on it, it'll send me to YouTube. Can you see the YouTube? It's coming up?
Yep.
Okay, very good. So this is something that I did back in 2008. And pretty much I'm going to repeat things, okay? So, oh, let me kill this thing. Let's get this thing back. Wait, not this. You can see my screen, right? Okay, so any one of these things that you see here, you can go to that YouTube, ignore any dates that I'm talking about, any sessions that today the power was off, so this is why we are starting from here, etc., because those are from 3 years ago, 3 years ago, whatever. Okay, so and it tells you which chapter of the book they're coming from. The first problem that we're going to do is coming from chapter 2, and the second 50 minutes is going to be chapter 5. Okay, so then we have a holiday. This is Victoria Day. You guys are off. Your section is off. And then we go to midterm on July 3rd. And at this point, you might as well forget everything about you learned before that. And then we come and do the rest of the course. Okay? Any questions so far? A simple yes or no will do for one person.
Nope.
Any? Okay, thank you. Thank you. Well, there's some important stuff here which probably you don't care about, but we have to include those. Now, there's going to be 10 assignments. And these 10 assignments, the way it's going to work is starting next week in the lab, I make a presentation in the first 50 minutes. And then at that point, we give you a problem. And there's going to be a GA there, and I'm going to be there. You start working on it if you want. I mean, nothing. I don't know how many people are here. Well, I have an idea, but I don't know. It's up to you because basically, we give you a problem at the end of the first hour. You work on it, ask us if you have any questions, and then you have 24 hours from the end of that lab to upload your work. And uploading your work, there is a template. There is a template that I've put in the resources, I think, or in the homework too, probably. And it's just 2 pages. You fill in those 2 pages, okay? And doing that, assuming that you have done the work yourself, is not going to take more than 3 minutes, okay? And then upload that. Make sure you also submit your part file as when you upload, not only that report, the part file and the analysis file that you don't know anything about. You're going to find out in this course. Okay, this is foolish. Midterm open book. Okay, of course, the final is open book, not cumulative. Now, notice that the midterm is 50%. Final is only 40. The reason is that midterm we have 7 weeks associated with it, and then the final is 40%. And by the time you reach the end of the term, some people who develop a hatred for a particular course, they lose interest, etc. Okay, so we put less emphasis on it. As far as this homework is concerned, there is a grading rubric that I've put on that template that you can look at it. Just to let you know, this is not because of the pandemic. When the course was done the last time, which was 2019, and the last 15 years, we did the same thing. Second hour of lab, after 50 minutes, we gave the GAs, or we gave the students a problem, and they had to do it in the remaining 2 hours. It's not that they could submit it later, okay? But this year, of course, you have 24 hours to do that at the end of the lab. But it used to be that the student would call a GA, the GA would go to their computer and see what they have done. And assuming that they have done it, not that it's kind of harder this time, but anyway, again, you don't want to cheat yourself, okay? you will be cheating yourself. Because when you go for a job interview, there's nobody there to help you. You have to answer specific questions. Okay, good. So that's this. If you miss the midterm, it's about things. You have a valid reason. I'll go along with it, and this is how it's going to work. Okay. Attendance. Okay, I don't know. Now, there are supplemental exam privileges here, and what happens in the case of supplemental exam? Some courses do not have supplemental exams, such as things that involve design, design and writing and things like this. This one does. However, basically what happens in that supplemental exam, I'll give you a test, 3 hours to do, both material from before the midterm and after the midterm, and your grade is solely based on that piece of work. The 10% assignment that you have done is not going to do you any good. If you did well on the midterm and then you somehow, unfortunately, bombed the rest of the course, you failed, God forbid, then forget about your midterm. You did well, great. You're already writing supplemental exam. It only the material on that test. Okay, so this is just so that you are aware of that, and that's pretty much it. Before I go to the other document, are there any questions? Any questions? A yes or no? I'll do it. From one. Thank you. I appreciate it. Okay, so I wanted to show you this other document. Let me see for a second. Well, actually, this is the stuff that I'm going to be doing today. There was another document. There is another document there which is titled "What You Need to Know About the CAE Course," and basically it's a summary of what we just discussed. Okay, so I'm not going to go through that. It's posted. If you want, you can look at it. So here is what we're going to do. Okay. Incidentally, don't shoot yourself in the foot. However, my intention is anything that I do for you, these presentations, the presentations in the lab, etc., in the lecture, these are going to be recorded and available to you on Blackboard. In other words, what I'm trying to say, okay, if you already had enough of this, you can go, you can watch the video. That's a bad strategy. Okay? All right. Already somebody logged off. Okay. Now, the problem that I'm going to do today, the first problem that I'm going to do today for you is this one, chapter 2. Okay? Now, the thing is, this course is not about you making complicated parts. I don't intend that you do an airplane wing or, I don't know, an instrument panel of a car, etc. Our geometries are simple. This is a simple geometry, okay? So the bar is made out of steel with these properties, and the bottom of this is clamped, and you apply a 5,000 or 2,000 pound force here. Now, this is a vague statement because when you say hit, when you say apply for 2,000 pounds, how do you do this? That's the whole problem with finite elements. The application of load, the information about the restraint, climate, these are all assumptions that we make. For example, I have to make, am I applying this load to the face? Am I applying it to the edge? Do I have, for example, a nail hammered into that thing and I'm applying it to the nail in the middle of that? So, okay, these are all assumptions that you have to make. When it comes to writing tests, I will not leave it to you to make that decisions unless it says it's up to you, okay? So anyway, this is a problem. And what we're going to do, the way we're going to create this geometry is we created a circle at the bottom of this, and then a path, and then ribbit, R-I-B. CATIA calls ribbing. In other software, it may be called extrusion or something like that. But CATIA calls it rib. Now, the whole idea of this finite element business is you break this object that you see here into little elements, little pieces, elements like this. And the ones on the left, these are 4 nodes. Each element has 4 nodes. It's like a pyramid type object. It's a wedge type object. And the one on the right, each element has that's, what is that? 8 no, 8, yeah, that's 8 nodes. Okay, actually, so this hang in there. There is 3, 6, 9, 10, because there is one edge at the back which also has a middle point, right? So that's 10 nodes, has 10 nodes, right? 1, 6 at the bottom. So yeah, that has 10 nodes. This one has 4 nodes. Now, in principle, the one on the right is more accurate than the one in the left, but it can be more expensive. In the simple problem that we are doing, it doesn't matter. But when you have 1 million nodes, then things become ugly. Okay, so now, and then do our analysis somehow. Basically, this FEA is presented to you as a black box. If you want to know what's inside of it, how it's done, when you have time, when you go to graduate school, you take a course in the theory and they show you all the math. Now, not all structures can be broken down into objects like this. You can, but it's going to be tough. So sometimes the structure is not modeled as a solid object like that, solid element, but as a plate perhaps, as a shell surface type element, or maybe as a line type element. So let me give you an example. Imagine that you put a load up there and you want to know what the deflection and the stresses are. Can you imagine taking this frame structure and breaking it up into little pieces like that? That's impossible. It's possible, but not on this planet. You need 10 billion elements, and then God knows what's going to happen. Okay, so you don't solve this type of problem with the element that I showed you in that particular. Or the other one is right here. Your favorite Mini Baja or Formula One, or for that matter, aero. If you're in an aero project, your airplane wing, whatever. Now, I have seen people taking this frame and breaking it up into solid element. Look at this. And because they can't handle it, they put one layer of element through the thickness, and then you get a good-looking garbage, nice colors, nice numbers, have no meaning absolutely whatsoever. So if you had to do this problem, you take the surfaces and mesh the surface. These are shell elements. Even these can be expensive. If you want to know deflection of a particular point, for example, this joint, when you apply some kind of load, actually you can break it up into beam elements. So you don't kill a fly with a cannon. These are important. But I've seen so many projects that because it's so easy, they just give it a surface like that and then say, oh, mesh it. And of course, because it can't handle it, you get a gigantic element here, and of course, everything is nonsense. Now, well, first of all, are there any questions? If there's anybody on the other side, I don't know. Okay, I assume there are no questions. All right. The other thing is that, okay, are we going to solve this thing as a static problem or a dynamic problem? Do you remember how much fun it was when you took Engineering Mechanics 1? It was fun, easy. But when you took dynamics, you surely looked at it differently. So the question is, am I supposed to solve this thing as a static or dynamic? Think about it like that. This object that I showed you, the bottom was clamped. And there was a load up there of 2,000 pounds. Where the heck did this 2,000 pounds come from? Did it happen by itself? it was created like that? Hell no. When you have a part and you want to put a load on it, there is no load on it to begin with. Then you push it a little bit, you apply a load, 10 pound, 100 pound, 1,000 pound, and 2,000 pound. So everything changes with time. So why are we saying anything is even static? If everything changes with time, that one that I gave you is also a dynamic problem. Well, yes, if you apply the load slowly, the deflection is going to be changing slowly. You can see that. See on the right side? It's changing with time. For example, this is the tip deflection on the top of the bar in the, I don't know, in one direction. It's changing with time, but look at it. The variation about a particular curve, that black curve, is almost non-existent, okay? So this problem, if the load was applied like that, and if slowly the deflection is going to be small, and at the end, when you reach the 2,000 pound, you're going to get the deflection not as a constant, but very close to a constant. It varies between, I don't know, maybe who knows, 1 millimeter and 1 millimeter, 0.001 millimeter, something like that. On the other hand, if you apply the load faster, that top load on the top of the bench rod, if I applied it fast enough, you will see that actually things change with respect to time. And if you give me the time, the load level, oops. Okay, all right, let's go back here. If you gave me the load level, that's not good enough. I cannot tell you what the deflection is going to be, because you can see that this load level, constant load level, will give you different things. This all has to do with how big this duration of the application of the load is. The most critical situation is when you take a hammer and hit the top with a hammer. You instantly apply the load, okay? When you do that, automatically it is a dynamic problem. If you don't hit it with a hammer, but apply the load fast enough, that's also a dynamic problem. But if you apply the load, it slowly, the problem may be treated as static. Nothing is static. Now, it has to do with T naught. And this T naught has to do with the natural frequency of the structure. Okay, this is why you do mass spring damper systems, because you want to get the natural frequencies of a very simple problem. And then when problem become more complicated, of course, its situation is more complicated also. It all has to do with natural frequency of the structure, the smallest natural frequency of the structure. Okay, let's move on. This is going to be the second part of the second 50-minute presentation. So we're not going to do that right now. I'm going to go and make the part. Okay, let me get rid of these. Can you see my CATIA screen, please?
Yep.
Yes. Okay. Very good. Very good. Okay. Are there any? If there are any questions, please don't forget to ask. This is a good time.
Are we expected to follow along with the construction of this part?
No. That's unless you're. I don't want to. Maybe you're very good in CATIA. I don't know you. Maybe you already know how to make that part very quickly. In fact, maybe doing it faster than I do. But I don't anticipate people doing that. Okay, this is why it's important to see this thing as a guideline. I told you it's important to hear it from a horse's mouth. then you can look at pictures, you can look at the book, you can look at the video, and you can make it. Doing it with me, it's inevitable that you're going to run into problem, and then you have to ask me, which is fine. There's nothing wrong with it. It's just that it's not very efficient. My suggestion is that for today, unless you're very confident in your abilities, go ahead and follow me. But I don't expect people to follow me as I'm doing this. Okay? Does that answer your question?
Yes.
Yes. Okay. Thank you. Okay. First of all, what you should do is you should start with a part file. Because when you start CATIA, usually starts with product, and I have no issue with it, okay? Anything that I do, instead of being a part, you can do it within a product. There's no problem, except that product are for assemblies. We are not going to analyze FEA. We're not going to do FEA of assemblies for another 3 weeks. To make sure that you don't run into problems, particularly on a midterm, when you have a part, start with a part file. Okay, so I'm going to start with a part file, new, and part. Part 1 is fine. Okay, that's good. Okay, very good. Let me remind you how you set your units if you don't remember it. And I don't blame you, because some of you, the last time did this thing was 2 years ago in Dr. Pushkar's class. So you go to Tools, Options, under Parameters and Measures. This is the units. Right now, on purpose, I changed this thing to millimeter because I'm going to change it back to inches. That problem that we're going to do is in inches. Units are specified in inches, and the force is specified in pound force. And the stress. Let me see now. Unfortunately, CATIA. There is no such a thing as a stress. They have it pressure. Pressure is PSI. I don't think they have a stress here. Let me check for a second. You can sort this out in alphabetical order. If you click on the magnet, it's already PSI, by the way. You can see that. But let me sort it out and see if I can find a stress. I don't know. Maybe they added it later. I'm not sure. So let me go and find the stress. Ah, very good. Excellent. They have it. They didn't have this thing in the older version. Okay. And yeah, so this is fine. Good. This is how you set your units. Now, the next thing that you do, you save your work. So File, Save Management. This is the name of the part, default name, Save As. I go to my desktop. I make a folder, new folder, and I'm going to call it May 10, May 10, Lab 53, 53, problem 1. Problem 1. And I say, okay. Oops. Okay, I'll put it there. Save. Okay. Let's check. So if I go to that name and this part is sitting in it. Okay, good. So let me, on the horizontal plane, I will sketch a circle. If you look at the problem description, the circle had a radius. It had a radius of okay, 1 inch. Okay, so I'm going to draw a circle on purpose. I'm going to center it at origin, make it oops, not this one. Make it 1 inch, radius 1 inch, diameter 2 inches. Diameter 2 inches. Exit. Okay. Good. Okay, now notice that on purpose, I'm going to center it at the origin. The more you're confident about your CATIA skills, the more of these special things that I say you can skip, okay? But I put it at the origin. Now, I want to draw the center curve of that object. And the center curve of that object was right here. Where is this? This guy, okay? This guy, 8, radius 1, and 5. Okay, so let's do that. So on a different plane, on that vertical plane now, I'm going to sketch. I'm just hoping that this thing is recording. I didn't stop the recording, so oh my God, I hope I did not. Okay, now notice that I said I insisted on putting the center of the origin at the center of the circle at the origin, and I insisted on drawing this thing starting at the origin. Now you can try putting this thing further to the left or further to the right. You see that at some point it will break down. You will not be able to create a model. Okay, so let me put these things here. So this guy, let me see now, the height from here to here was 8. This radius was 1. This radius was 1. And the distance from this thing was 10. The distance from here to here is 10. Oh, not sure, not 10. It's 1. It says 1. And I'm looking at the draw. No, it says 5. 5. And exit. Okay. And can anybody tell me what do I have to do to make that part here? Can somebody tell me that? Don't be shy. I don't know who you are. Say that again. Sorry.
Is it the sweep function?
There is no sweep function in CATIA. Well, at least, yeah, there is no sweep function here.
Could you rib it?
You have to rib it.
Yeah, ribbon.
Ribbit, R-I-B. Yes, yes. Now, in all likelihood, maybe you're talking about your SolidWorks thingy or some other package. They may call it sweep or extrude, etc. CATIA calls it rib. Rib. I have to be careful here and read this thing carefully because cancel that. Because this one was selected. That's why it gave me some weird, warning message. So rib, and you have to read this thing carefully. It says, what is the profile? The profile is that circle down here. What is the center curve? In some other packages, they may be calling this thing a spine. And there we are. Believe me, if that center curve, I had put it too far away to the left or too far away to the right, it would have bombed out. This would have bombed out. It would not have worked. Okay. All right. So save, and we saved it. If you give me 1 second, I want to go to my screen, make sure this is recorded. Should I take my chances? Yeah, I'll take my chances. I didn't stop it, but who knows? We'll see. Worst come to worst, if this thing is not recorded, tomorrow's lecture, lab 54 will be recorded. Is there a way you guys can check
Professor,
that?
it's recording.
We can see that
Excellent.
it's recording.
Thank you. All right. Okay, now, the next thing you have to do is to say what material is this thing made of, okay? So that is done in this icon. It looks like a ball being dropped into a box. I'm sure Dr. Pushka has talked about these things to you, but you click on it, and we're using a metal tab, and we're using a steel. On that part, notice that now you can close it. Now, this is steel. Double click on it. These are the default properties of steel in the CATIA database. Okay, just bear with me for a second. This is going to pop up. Okay, come on. All right. Under the analysis tab, notice that there is the Young's modulus, there is a Poisson ratio, there is density, etc. Now, in the statement of the problem, I'm saying the Young's modulus is 30 e to the 6. So you know what? I can change it right here. 30, if I want to be very finicky about this, 30 e to the 6, right? E to the 6. E to the 6. 30 million psi. And the Poisson ratio, I'm saying 0.3. I will not do that to you on the tests because I'm just telling you where you can change these. On the test, I'll say default properties so that you can skip one step. Now, this density is not relevant because this is a static problem that we are doing, and there's no weight involved, so that is irrelevant. All right, save everything. Okay. Now we're going to go to generative structural analysis. Now, my screen is, my CATIA interface has been customized. So for you, if you're doing this thing for the first time, you go to analysis, generative structural analysis, okay? So what happens, CATIA sees a solid object, immediately it jumps on it and breaks it up into those little elements that I was talking about. Okay, see, it takes this and breaks it up into stuff like that, that size, roughly that size. By the way, we are doing a static problem, so static analysis, so okay. Now, I don't like this material shading, so let me change my, take this thing out of here. Let me change my my shading to with edges, okay, good, or with you know, not material. And if you want to see your mesh, you put the cursor on this line, nodes and elements right there, right click, mesh visualization. So it breaks it down into little pieces like that. Okay, now if you want to change the size of this, I'm going to double click on that, double click on octree tetrahedral element, and you can change the size. For example, I can go to 0.3, I don't know. And then you can choose linear or parabolic. Okay, so here I've chosen parabolic. On a test, in all likelihood, I say use default linear element. Unless we specifically ask you to change it to parabolic, then there you leave it the way it is. Look, it's so much tinier right now. Right click, where is that? Put the cursor on nodes and element, right click, mesh visualization. There we are. Now, there is something else that I'm going to show you that is not discussed in the in this problem, but here's the situation. First of all, let me deactivate the mesh so that I don't see it anymore. Right click, deactivate, or delete. If you delete it, okay, then you have to do it again. There's no problem. But suppose I want a finer mesh on this surface. Suppose I want it. How do I do this? This is fine for most of it except for this area. So when you look at the model manager where there's a traffic light here, traffic light, see that? Second toolbar, there is an icon which says local mesh size. Local mesh size. You select it, it says, okay, you want me to concentrate on a particular area? Go pick it. Well, I said this area, right? I said, I want to find a mesh on this area, right there. And it says, okay, this is the value that I had from the guy who used this software 2 weeks ago. And he put he or she put 0.2. Is that what you want? Look, it's smaller, right? But I want it to be even smaller. How about making it 0.02? It's very tiny. You don't have to do that here. Look, it's there. Believe me, it's there, right there. You see it, right there. Terrible. I don't want to do that. Double click on it. Let me make it 0.09. How about that? That's a little bit better. Okay, you want to see it? Right click, mesh visualization, or activate the mesh. So you know how to refine the mesh if you're asked to do. And you will be asked to do that on your first assignment. And if you change your mind, just delete it. Just delete it. Okay, it's there. The original one is there. Okay, we have 5 minutes to finish this, and then whatever is left over after the 10-minute break, we're going to come back and finish it, and then go to the second problem. Now, the bottom of this is clamp. You see, in CATIA, There is the mesh. This is where you do the mesh. There is the restraint. Restraints mean roller, clamp, etc., etc. And then there is the load right there. So clamp is what they taught you in engineering. Nothing moves. This is an idealization. There is no way in the world we can clamp something to something else. How are you going to make sure that this thing is not moving? Well, you use glue. You use welding. You use, I don't know, soldering. But then, even then it's going to change because attached to the ground, attached to some other part, that will move. So this will move. So this is an idealization, okay? Now, the load, look at the load toolbar. This is pressure. Pressure is on surfaces. I don't want to apply a normal pressure. Pressure is always normal to the surface. I don't want to do that. I want to push it this way. So the way I'm going to describe it to you is use the force, distributed force. On that face, now here you're going to make an assumption. Am I doing it on the face or am I doing it on the edge? None of them are necessarily true. The real life problem is something in between, okay? Now, in the direction, you look at coordinate system here, in the direction X, not Z. Katia doesn't forget the stuff that people put in it before. So it's going to be minus 2,000 pounds. 1,000 pounds. You say, okay, right there. Isn't that what you want? Yeah, okay. Now, do not forget to save your analysis. You saved your part, true, but not the analysis. So you go to File, Save Management. There is my part, but there is the analysis. There is the analysis. This should go in that folder. Save as. In that folder, this is the folder that I moved, and it's a good idea to give these things meaningful names. So, for example, what was that? May 20, oh, May 10, lab 53 underscore problem one. And the default is analysis 1. So it's up to you whether you keep it like this. You can call it analysis 15. You can take the 1 away. This is what describes your analysis. A lot of people, or some people, forget to do this. Everything looks good on the screen, and then when it is submitted, they don't submit the analysis file, okay? And there is no way for us to know what you have done. We can mark your part, but not your analysis. Okay, that's it. Now we're going to run it. Calculator. This looks like a calculator. This is should have been a run. Should have said a run, but it says compute. And say okay. After this thing runs, we're going to take the 10-minute break, and we come back at 5 o'clock. Okay? Just bear with me for a second. Say okay. Okay. Just 1 second. Yeah, say okay. Is that what you were asking?
I thought you told us to say okay, so I said okay.
Yeah. Good. Excellent. Somebody's following me. Very good. Okay, deflection. How does it look? There we are. Can I animate it? That looks right. It looks right. Doesn't mean it's right answer. Okay. So last thing that I want to do right now before the break, plot the 1 meter stress. Let me change the rendering so that you can see the stuff in a shaded contour form right there. All right, folks, listen, it's 10 to 5. Let's take a 10-minute break. We're going to come back and do the rest of this. And I'm going to stop the recording. When we come back, I'm going to start it again.